Hello everybody, and welcome to oral session 4 today on running and the upper body. We've got 4 speakers today. We've got Harper Stewart, Emily McClelland, Casey Weems, and Moira Prihoda. Please correct me if I've pronounced that incorrectly, so sorry about that. We will be taking questions after each oral presentation. So if you have any questions during the presentations, please just pop those into the chat and we can read those out after each speaker. So first up, we have Harper, who will be presenting on the changes in 800-metre personal records for competitive female runners from high school to college. So Harper, if you'd like to try and share your screen. And I'll just get, if anyone has their microphone still turned on, I'll just get you to please mute yourself throughout the presentations. Alrighty, we can see that, Harper. When you're ready, you can take it away.
So can you hear me?
Yeah, we can hear and see you.
Okay, cool, thanks. Yeah, thank you so much for that introduction. My name's Harper Stewart and my pronouns are she, her, hers. I'm a third-year PhD student at the University of Southern California in Los Angeles, and my faculty advisor is Dr. Jill McNitt-Gray. So today I'm going to be talking about one of the challenges that we commonly face in our lab, which is finding a way to effectively communicate our scientific findings to our athletes and coaches that we're commonly working with. And so in some of my previous work, we've been doing a longitudinal study of collegiate runners. And these collegiate runners, they're very busy. So it's very important for us to be able to provide value to them through our analysis. And it's important for us to be able to demonstrate to them quickly and clearly why biomechanics is going to be important to what they're doing. So in order to find a way to effectively engage with our athletes and coaches, we wanted to try and use some of their performance results from prior races to help form connections with them. So we thought that by answering questions that the coaches might have to help assess their training programs would help provide more opportunities for us to develop relationships by answering their questions and providing more value to them. So using this performance data is also really helpful because it's something that they're really familiar with and use every day. And sometimes when we're coming in with biomechanics variables and different things that we're familiar with scientifically, it can be hard to get everyone on the same page. And then additionally, we also know that it's very difficult to get biomechanics data, but this results data can be a little bit easier to get and provide some context to information that we might already have. So where are the different places that we can get this data? Specifically for athletics, some examples of places would be World Athletics, Keepers, and MileSplit, which all are websites which compile different performance results. Some previous work that's been done has looked into how many races before an athlete is ready to peak for their season and set a personal record. And then other work has looked into the likelihood of an athlete making it to a high-level competition. So for example, NCAAs in the United States would be the example of the highest level college competition. And so having the answers to these types of questions can help us to support our athletes and coaches that we're working with. So the overall goal of this study was basically to use it as a pilot for showing the value of this type of analysis and come up with a sample set of questions that a coach might be interested in looking at. So our population was female 800-meter runners. And our first question was, does this particular population of runners get faster as they're transitioning from high school to college? And so logically, we would think that this would be the case. You know, someone's moving into college and they have a new coaching staff and additional resources. So we would expect them to get faster, but we have to look at the data and see what that's actually showing. So the convention for how we're reporting is we took the high school personal record time and subtracted the collegiate personal record time. So if the person had a positive PR difference, this would indicate that they're going to be faster when they get to college. The second question that we wanted to look at was, does conference size influence an athlete's PR difference? So we looked at data from 3 different conferences, including the Pac-12, Big Ten, and Patriot League, which are all 3 different conferences from the NCAA Division I level, which is basically the highest level of collegiate athletics in the United States. The Pac-12 conference was of particular interest because athletes that participated in our longitudinal studies were from the Pac-12. And then the Big Ten is another large conference that's very comparable to this Pac-12 league. And then the Patriot League is representative of a smaller D1 school, which was interesting, basically because we wanted to compare how this would stack up against other bigger D1 schools. So with this, we wanted to assess if the margin of improvement for PR performance was different between these collegiate conferences. So we would expect that if you're at a smaller school, you would likely have slower PRs from high school, and you would have more space to grow as you're moving into college. Versus these larger D1 conferences, you would have to have a very high school level performance in order to compete or get recruited at one of those schools. And it would likely be harder to improve because you're already at such a high level competitively. So our final question was, do these faster high school runners continue to be the fastest runners in college? And is this relationship linear, and is it consistent for this particular sample of athletes, or is there something else that's going on with the data? So in order to answer these questions, we gathered information from the 3 outdoor championship results in 2019. So there were 84 women that competed in the 800 meters across these 3 conferences for their championships. Unfortunately, there were 11 athletes where we were unable to find their high school or college PR in order to answer our particular questions. So we ended up with an overall sample of 73 athletes. Then for our results, we did find that there was a significant difference between high school and college PRs for the overall sample. So the trimmed mean for an individual PR difference was approximately 4.4 seconds. So our typical athlete was improving by around this margin as they went from high school to college, which is pretty exciting. And then there were approximately 80% of the athletes improved their personal best by over a second as they moved into college. So overall, our main takeaway was that most of the athletes were showing an improvement from high school to college. This is the same results, but just broken down by the 3 particular conferences. So we found that this finding from the previous slide was also true across each individual conference. But what was interesting was that there was less variability in the data from high school to college. So you can see there's greater variability in the high school data versus the college data there. Then for our second question about, does conference size influence PR difference? It was really interesting that we found that the typical improvement was similar across the 3 conferences. So you can see our 20% trim mean is indicated by the black dot on each of the sample data, each of the conference data. So it's interesting that conference did not influence basically the athlete's margin of improvement, but there was very different distributions in the data. There's a wide variety across the Patriot League. And then finally, for our third aim, we found that there was a positive trend in the data when we looked at the high school PR times versus the college PR times. And so the athletes that started with faster high school PRs typically ended up with faster collegiate PRs as well, which is indicated in the lower left corner of the graph. But what was interesting is when we used our running interval smoother, if we looked at the 25th and 75th percentiles, you can see that there is a larger range for the athletes that started with a slower high school PR than for those athletes that started with a faster high school PR. So those athletes that started with slower PRs showed more variability in their improvement as they went from high school to college. This is an overall just summary of our major findings, which is in the typical format that a coach and athlete might use, which is also published in the conference paper if anyone's interested. So overall, we were able to verify our first hypothesis that athletes did improve their times as they transitioned from high school to college. We did not verify our second hypothesis, and we found that it was interesting that the margin of improvement across the 3 conferences was largely the same. And then we did see a positive relationship between high school and college PRs. However, this wasn't like a perfectly linear and homoscedastic relationship. There was some heteroscedasticity and different variability in the ranges depending on the starting high school or college PR. And then so some limitations of this approach, we only took athletes that competed at their conference championships, which isn't representative of the entire team. We also only looked at female athletes, but obviously a similar analysis could be done for male athletes, athletes in other events, and also other sports. And then we only chose to look at these 2 points in time with the 2 PRs from high school and college. And then this also doesn't tell us why that athlete may have improved or didn't improve when they got to college, but it does provide more motivation for additional biomechanical analyses to help us figure out why their performance data might be changing. And then, so what is the value of putting an athlete's performance data in context? So this can help us to assess performance over time within an individual and also across athlete populations. So an athlete could take their individual data and also see how they're comparing to the typical athlete in their conference, like what we tried to do with our example. It also can help us to engage and develop relationships with coaches and athletes, which is helpful for our work. And then it can also help coaches to make informed decisions with evidence-based practices that's actually based on the data. And then also provides context for us as biomechanists by helping us to put the longitudinal information that we'd be collecting over time into context with more metadata by knowing more information about our athletes. So overall, we thought that this was a pretty useful framework for evaluating an athlete's performance over time, and we hope that others find it helpful as well. These are my references that were used, and I'd like to acknowledge the other members of the USC Biomechanics Research Lab and also my funding sources. I can take questions at this time. Thank you so much for your attention and for the opportunity to present here.
That was a great presentation. Thank you so much, Harper. If anyone has any questions, feel free to just pop them into the chat if you'd like. I just had a question. You said that at the beginning that this was part of a pilot study. Can you give us a little bit more context to that? Are you going to be looking at males or?
Mm-hmm. Yeah, so this was just kind of like an overall experiment to see if we could basically figure out how to do it and like set up the processes for it. So we have another study that has to do with a population of Pac-12 collegiate runners. And so we were trying to understand more about their performance data to basically put that data into context. So this was kind of like a smaller side project to see if we could supplement that information.
Okay, great. And then Claire's got a question just saying, given that the collaboration and communication between coaches and biomechanists was key to the justification for this study, what role did the coaches play in terms of shaping the design and aims of the study?
Yeah, that's a good question. So we didn't actually consult the coaches for this particular study. It was kind of more of a hypothetical of, we think that this might be the type of questions that coaches would ask. But in the future, we would want to consult our coaches moving forward so then we could figure out how we could use this analysis to benefit them and actually answer the questions that they're interested in.
Yeah, awesome. If we don't have any more questions, we'll move on to the next presenter. Thanks so much, Harper. That was great. Our next presenter is Emily McClelland, sorry, and she'll be presenting on cutting sex performance differences down to size. Are females closer to males in shorter sprint races? So, yeah, we can see your presentation now.
All right, good. Can you hear me?
Yep, I can hear and see you. Take it away, Emily.
All right, awesome. Thank you. Well, thank you guys very much for having me. Like she said, my My talk is entitled Cutting Sex Performance Differences Down to Size Are Females Closer to Males in Shorter Sprint Races. My name is Emily McClelland, and I'm in the Locomotor Performance Lab at Southern Methodist University in Dallas, Texas. I'm going into my 4th year of my PhD here with my advisor, Dr. Peter Wayand. So to start, differences in sport performance between men and women have been of interest and marked since women formally started competing in sport decades ago. And running performance has been of specific interest, especially in early analyses of these differences between the sexes. Early speculation of these differences, published by Whip and Ward in Nature in 1992, looking at world record progression throughout historical time between men on the left and women on the right, looked at those rates of improvement of performance in different running events. And they actually speculated by extrapolating those rates of improvement to a possible convergence of performance in running at some point in the future in these different running events. But we know that there are a lot of different factors that went into that rapid increase in performance for women early on in their formal participation in sport, like cultural acceptance of women participating in sport. That rapid improvement had a lot of different factors playing in. So extensions of this type of analysis, one by Chevrant and colleagues in 2005, showed that these performances and this improvement kind of leveled off, especially in the 90s and into the thousands, into the 2000s here. You can see on the right, this is world record data over historical time there, and you can see the plateaus in both men in the triangles and women in the circles. And another analysis by Seiler and colleagues in 2007 also concluded that they included not only world record data but elite performances as well. And they came to the conclusion that these running differences between the sexes is pretty stable, and that we're reaching a point in time where we're able to analyze an intrinsic sex difference in these different running performances at this point in history. So it's important to talk about the different the different bases for performance between different types of running events. And so to start, we'll talk about endurance-based events. And we know that for endurance running, the main determinant of this type of performance is energy in versus energy out. So energy supply and energy demand. The basic difference between men and women in these endurance types of events is about 11%. Men run 11% faster than women, with very little variability in endurance type events. So anything 800 and above, that's endurance. And we know that this difference in men and women in fat percent or in percent fat exists as well, and it's about 11% also. And so this causes women running at the same speed. If they're to run at the same speed as men, it costs them more energy per kilogram of body mass to maintain that speed versus men. And this has been supported by classic work by Cureton and Sparling, where they loaded men up to the same non-functional mass as women, and it slowed them down and caused them to have a greater energy expenditure per kilogram of body mass than women. But that's obviously not the whole story. Men also have a greater hemoglobin content than women overall, so they're able to get oxygen to their muscles more effectively and efficiently. So that's kind of the basis for the sex difference in endurance events. For sprinting events, though, this sex difference has received a little bit different or a little bit less attention. And for these types of events, there are different limiting factors to sprint performance, and they're mainly mechanical factors, not metabolic factors. So we know that sprint performance is limited by the amount of mass-specific force athletes can put into the ground in a short amount of time. We also know that the shorter the race, the greater proportion of that race is devoted to accelerating one's body mass. Acceleration conforms to Newton's second law. Acceleration is equal to force divided by mass, so mass-specific force. It's been shown that smaller individuals have a greater capability to produce mass-specific force, especially in weightlifting. So this work by Ford and colleagues in 2000 shows that there is a relationship between smaller individuals being able to lift more weight per body mass than larger weightlifters. And so that's kind of a support for the fact that smaller individuals might be able to produce more force per kilogram of body mass than larger individuals, thus possibly affecting the difference between men and women in sprint races. So this led us to our question of, does the sex performance difference in sprint events vary with event distance? Could being smaller provide a possible advantage in these shorter events? And our hypothesis was that smaller females would perform relatively closer to males in shorter sprint distances. And so we went about analyzing this by collecting or gathering the top 40 race speeds for males and females using World Athletics top lists in a 15-year period for the 60, 100, 200, and 400 meter races. We found these individual athletes' heights and masses from other public sources. And then we analyzed the percent difference in performance using the equation right there. We analyzed the relationship between athlete height and event distance using a simple linear regression, the differences between male and female race speed using independent sample t-tests in each event. And we also looked at the relationship between race distance and percent difference in performance using a simple linear regression. And so what we found was that the men were 7.1% taller than women overall. We found that there was a significant trend for both sexes for height in relation to race distance. And you can see that those trends represented in the graph to the right. We've got athlete height on the X and event distance on the Y there. Men are blue, women are red. The shortest athletes for both sexes were found in the shortest race distance. So in the 60 for both males and females, the average height was the shortest. Race speeds were significantly different for males versus females in each event, which is not surprising. For the 60, we had, and that relationship between percent difference in performance and event distance was also significant. So we found that in the 60, that men ran 8.6% faster, the 100, 9.2% faster, and the 200, 10.4, and the 400, 10.9% faster. And this is using average speed of the race within those 40 individuals per event. And then that relationship is pretty consistent that relationship between performance difference and event distance is pretty consistent with an R squared of 9.7. So to sum it up a little bit, shorter athletes specialize in the shorter event distances. That percent difference in performance relationship to distance is very consistent. And we also found that males and female performance differences was smaller for the shorter versus longer races. So to conclude, body size varies with event distance. So we found that those smaller athletes do tend to be in the shorter races. This could indicate some sort of event-specific mechanical demands, just because we see those specializations in the shorter events. We also found and supported our hypothesis that women perform relatively closer to men at the shorter race distances, and this could possibly be because of smaller individuals being able to produce a greater mass-specific force per kilogram body mass. So that could drive their difference or that difference to be smaller in performance. But obviously we didn't test that. This is just a speculation that could be why. And this could apply to other sports where there's more relative shorter distances to run within the event, like in soccer where there's more acceleration-based running versus other things that include more endurance type events. So thank you guys so much for your time. I appreciate being able to present, and I'll take any questions at this time.
Great presentation. Thank you so much, Emily. Do we have any questions? If so, you can just ask those via the chat. I was just wondering, do you have any intentions of looking at this relationship in terms of like body mass or any other composition measures?
Yeah, so we have some. This is a kind of a first look at this type of sex difference. the next step is going to be looking at even within race differences,
Yeah.
and also then looking at how the percent difference in body mass and in body fat and also muscle mass plays a role in those differences. But that's a next step for sure.
Yeah. And so whereabouts are you like pulling the, I guess, the body
mass data? A lot of
yeah,
it has been from, there's a Norwegian site. I can't remember I can't pronounce the name of the site, but they collect a lot of demographic information on Olympic athlete or track athletes. So I found a lot of it there. And then different teams, different national teams have their heights and weights listed for some of their athletes.
Yeah.
And that's where I've kind of found them.
Yeah. Have you been trying to like, I guess, match them within a time frame?
As of right now, not for this data set. And that's something that we need to do further down the road, is to make sure that those, especially the weights, need to be current with what they're doing race wise. It's interesting. It's going to be a challenge to do that, but definitely needs to be done.
And we have a couple of questions in the chat just quickly. So Harper's asked, what are your thoughts about Usain Bolt's height relative to your overall findings? Is he a major outlier?
He is really tall for that's why he was in the presentation multiple times relative to Shelley and Fraser, because their height difference is so stark. And they're both some of the best in the world at that specific event, the 100 meters. And he is really tall for what he is. So he's not, he is an outlier, I would say, for what we've seen in those 100 meters. And he looks tall on the starting block compared to other athletes there. So.
Yeah, awesome. Thank you guys so much. Oh, sorry. Thank you, Emily. And thank you everyone for their questions and comments. We're just going to jump to the next presenter now, which is Cassie. Was it Casey?
Casey, yeah, Casey.
Casey, awesome. So Casey's presenting on the coordination of center of mass velocity and upper extremity kinematics during basketball shots from two distances.
Let me stop sharing, sorry.
Yeah.
All right.
Cool. Fantastic. We can see your screen. Yep.
Perfect. All right. Well, thank you. And thank you everyone for stopping by for this presentation, which will cover some coordination of center mass velocity and upper extremity kinematics during basketball shots from two distances. So in the basketball shot, the goal for the shooter is to release the ball so that it flies through the air and hopefully into the hoop. And so as it flies through the air or its ball trajectory, it's determined by the resultant velocity and angle, as well as its position relative to the hoop, all that ball release, and any air resistance that it may encounter along the way. The ball velocity at release is contributed by the center of mass velocity's contribution, as well as the arms. The center of mass velocity is generated during ground contact during the shot preparation phase, and then decreases once the shooter is in the air. The arms contribute to the ball velocity through its rotational characteristics. And then there are more than one way to achieve the task to successfully shoot a basketball. And we can see here various shot trajectories that end up being successful from different distances as well as different individuals. Even from the same release position, we see that there are multiple trajectories that enter the hoop. There are also numerous combinations of joint configurations and joint angular velocities that will result in a successful shot. We also know that shot distance affects the whole body and arm kinematics at the ball release. It's been found that with an increase in shot distance, the ball velocity increases, the body center of mass vertical velocity increases, the shoulder and elbow angular velocities increase, and the time that the person spends in the air decreases prior to releasing the ball. So all of these are important factors that will have some role in determining if the shot is successful or not. However, they're just at an instant. So we're curious if the full generation of the whole body and arm velocities during the basketball shot change with a change in shot distance. So our aims were to analyze if coordination can be characterized by plotting these velocity signals against each other, and if these patterns change with a change in shot distance. We hypothesize that each individual will have their own unique coordination pattern, and that yes, the shot distance will affect the coordination patterns, either during the shot preparation phase or during that push action on the ball. So we had 7 recreationally skilled individuals shoot at least 10 shots from the free throw line, as well as the American high school 3-point line. We are only analyzing made shots. For the center mass vertical velocity, we use 2 portable force plates in which we use the net impulse equals change in momentum theorem to calculate it. For angular velocities, we attached wearable sensors to the upper arm and forearm, and then we reorientated the angular velocity signals from their local reference system to the gym reference system. And so in this presentation, a positive angular velocity is a clockwise rotation. And then for coordination, we are defining it as the pattern between the center mass velocity and the upper body angular velocities over time. Here, we're just going to take a look at one shot from one individual so we can hopefully get a better understanding of what these patterns look like, because they can be quite overwhelming if not given some context. So here in this bottom left quadrant, we're looking at the forearm angular velocity versus the center mass vertical velocity. The bottom left quadrant, this would mean that the individual has a negative center of mass vertical velocity with a upward and backwards rotation of the forearm in a counterclockwise manner. Once it gets into the upper left-hand quadrant, the center of mass vertical velocity is now positive, while the forearm is still rotating counterclockwise. Then eventually it will end up in the release, ball release, which the center of mass vertical velocity will be positive, and the upper arm will now start to rotate towards the basket in a positive rotation. So this plot is going to be synchronized with the video shown, and this orange dot here will follow along with the video. It'll start about 0.6 seconds prior to ball release. So we can see here that it's negative as they drop down until they reach a low position, in which the center of mass vertical velocity will become positive on its way to the maximum, which is right around the time of ground departure. And then the forearm will start to begin to rotate towards the basket, eventually getting to ball release. All right. And we'll do the same thing this time with the forearm angular velocity and the upper arm angular velocity. And when in the bottom left-hand corner, both the upper arm and forearm are rotating in a counterclockwise manner. This upper left-hand quadrant would mean the forearm is rotating clockwise while the upper arm is rotating clockwise while the forearm is rotating counterclockwise. The upper right corner would be the upper arm and forearm both rotating in a clockwise manner, while eventually we'll get to where ball releases, where the upper arm is going up and back in a counterclockwise manner, while the forearm is going rotating forward in a clockwise manner. So again, it's synced up in time. I'll start here pretty quickly. We can see how coordinated the forearm and upper arm are together during this arm swing during the jump. The elbow is likely fixed, the elbow angle is likely fixed, and it's just the upper arm rotating about the shoulder joint. Eventually until the forearm starts to begin to rotate towards the basket on its way to ball release. All right, so now we'll actually start to look at some plots of all the individuals. These plots here are the median patterns for each individual. The gold pattern represents the shots at the free throw line, and the blue represents the shots at the American high school 3-point line. Here we're looking at the upper arm angular velocity versus the center of mass vertical velocity. And what you can see here are vertical dashed lines representing around the time that the person leaves the ground in their jump shot. We can pick up with this coordination or like these patterns that we're looking at, we can pick up pretty distinct coordination patterns between two different groups. One group that uses their arms to swing or to help generate that force during the jump. This will likely help increase the force that they generate on the ground during the shot preparation phase. This can be beneficial because it will lead to a greater center of mass vertical velocity when the person leaves the ground. And having that is also beneficial for a variety of reasons. One would be it potentially provides a greater ball release height, so you could shoot over a defender if somebody was in your way. Another reason is that a greater center of mass velocity at ball release reduces how much the arms actually have to contribute in generating the full amount of the ball velocity at release. And then also it's helpful as if you were to increase the shot distance, if the center of mass vertical velocity is greater, then it can just help create a greater ball velocity at release to help it get that extra distance. So here we can see this coordination pattern and these 4 individuals compared to these 3 on the right, where they use no arm swing in their jump. So that means they got their arms up and set prior to actually performing a more down-up counter movement jump in their jump shot. If you're looking at forearm angular velocity on the x-axis versus the center of mass vertical velocity, we pick up some key timing characteristics in some groupings. So here we find 4 individuals that are actually start that forearm rotation forward towards the hoop after they leave the ground, while 3 individuals are starting that forearm rotation towards the hoop prior to leaving the ground. It's likely that when you're starting that forearm rotation prior to leaving the ground, means that you will end up releasing the ball earlier relative to that center mass velocity, or closer to it, that maximum center mass vertical velocity, which again would either, 1, contribute more to the ball velocity, which reduces how much the arms actually have to contribute, or just allow you to shoot from a further distance because you have a greater ball velocity at release. Some key things and changes in shot distance we see from these 3 individuals here, that they actually change and release the ball or start that forearm rotation earlier relative to their center mass vertical velocity maximum, or when they're leaving the ground, as well as, and then that's in opposite of what we find in these 2 individuals, where they're starting it later relative to them leaving the ground. Just identifying one individual in particular, we see some key changes going from the free throw line to the American high school 3-point line, and that in the gold here, they're actually starting that forearm rotation towards the hoop after they leave the ground, but yet when they step back almost a couple meters to the 3-point line, they start that forearm rotation towards the hoop prior to leaving the ground, pretty good prior to leaving the ground, which again will likely result in them releasing the ball with a greater center mass vertical velocity. Now, if you were to look at the forearm and upper arm angular velocities together, it's pretty, we again find 2 different types of patterns, or one very identifiable pattern during the shot preparation phase. And that's particularly with those that actually utilized an arm swing during their jump. And that would be these 4 individuals here, just in that down and back coordinated action. We also, again, highlighting one individual here where we're looking at differences between the jump shot at the free throw line versus one at the 3-point line. And here, the upper arm angular velocity is hovering right around 0, which means the upper arm has basically stopped its rotation, and then the forearm begins its forward rotation about a fixed stopped upper arm. However, when they step back again to the 3-point line, they're actually utilizing more of an upper arm rotation, which likely helps contribute to a greater ball vertical velocity, helping it reach that extra distance. Other than that individual, the coordination patterns between shot distances for all the remaining individuals are pretty similar. So here, if we were to put them all 3 together and analyze, or be able to view participants in each of the 7 columns, we can see how unique some of these patterns are compared to each other, and how they may change based off of shot distance. The reason why some of these may change based off of an increase in shot distance are likely due to the increase in center mass vertical velocity, as well as an increase in upper arm and forearm angular velocities at ball release, which has been shown previously in literature. The coordination patterns, again, were pretty unique to the individuals, and for the most part, pretty similar across distances, especially during the shot preparation phase. So in this study, we analyzed how, if we could identify some coordination patterns within individual and how that may change when increasing the shot distance from the hoop. We found some pretty similar patterns within the individual, and we found some key or some interesting findings looking at the timing of that forearm forward rotation relative to when they left the ground, which again would likely lead to a greater center mass vertical velocity at ball release, which again can be helpful for potentially getting a higher release height, as well as potentially contributing more to the ball velocity and reducing how much the arms have to actually contribute. By looking at these patterns, especially at a more individual manner for each participant or each player, we can understand how the individual is actually going about accomplishing this task and how certain task constraints like increasing the shot distance may change their behavior. So if we are looking to teach somebody to shoot from a further distance, being able to look at how these velocity signals and how it's contributing to ball velocity may change when you increase the distance. We look to expand on this exploratory work in the future by increasing the sample size, increasing the shot distance, especially to something closer to their max capacity, and then also increasing the number of successful shots. We'd also like to analyze a more experienced population, as well as hopefully make it a little more realistic by adding a defender in this and seeing how a defender may affect their behavior. So with that, thank you for your attention and taking any questions now.
Thanks, Casey, for a great presentation. If anyone has any questions, just pop them into the chat. Have you looked at any of this in relation to successful or unsuccessful shots? Like was, a particular arm swing or a push on the ball before or after associated with better shooters?
Mm-hmm. Yeah, we have not quite done that. That's definitely a good point and something to look for in the future. It's a bit tricky because we have such limited number of shots anyways, and thankfully most of them were successful, at least for something like this. Hopefully by increasing the number of shots that they take, we'll be able to make better comparisons on mixed versus misses for sure.
Yeah, it'd be really interesting to see whether any particular coordination patterns are associated with successful or unsuccessful shots.
For sure.
Did we have any questions from the audience? Awesome. Cody, so based on what you looked at, how do you think the differences in technique influences the ball flight characteristics, such as the release angle, angular velocity, and ball velocity and success?
Yeah, it's another good question. Yeah, as far as the angle that the ball is released, it's a bit tricky because even though we have the angular velocities, we don't have the angular positions of the segments to understand how exactly they're contributing to, say, the vertical or horizontal. Eventually we could start to look more into that. One of the main characteristics that we can pick up here is how people will utilize their arm swing during the jump and potentially generate more of that force production in the ground during the shot preparation, which again could lead to a greater center of mass velocity at ground departure, which could lead to a few potential benefits. Again, higher release height or more contribution to the ball. But also some of the other things that we found, especially when we identified that one individual where at a closer shot to the basket, they basically fixed one segment and allowed the other segment to rotate on top of it. But then changed it when you changed the shot distance to a further distance. So I'm not sure if that directly answered the questions, but it's, yeah.
No, they're interesting insights. Thanks, Casey. Do we have any other questions before we move on? Give it a second, and if not, we'll move on to Moira next. Good to go. So yeah, if anyone else has any other questions for anyone, by all means, please feel free to pop them into the chat where they can also respond. But Moira, if you'd like to get ready, looking at, so Moira's presentation is on handstand balance motor control mechanisms.
All right, great. Can you see my presentation?
Yep, we can see you and hear you. Take it away.
All right, great. Well, thank you for the introduction. And before I begin, I'd like to thank my co-investigators, Carl Newell from the University of Georgia and Gareth Irwin from Cardiff Metropolitan University. So before we talk about handstands, I'd like to start with a brief introduction to postural control. So humans develop balance control strategies in postural stances by organizing muscular contractions to create torque about joints with the goal of controlling the global variable of center of mass. And this presents as a cycle with even small changes in center of mass location triggering muscle contractions to recenter within the base of support. This stepwise system is complicated by linked segments that create many degrees of freedom in which a single muscle contraction influences multiple segment and joint orientations. The handstand is an example of a postural stance in which a balance control strategy must be produced to maintain the inverted position. And the reason we're interested in the handstand is because it's a fundamental skill in gymnastics due to the association with many complex skills and the fact that it's performed on all apparatus in both men's and women's gymnastics. There are 4 joints, namely the wrist, elbow, shoulder, and hip, that are available to assist in handstand postural control strategy. And previous work has focused on the sagittal plane, in which torque about the wrist has been found to be the most prevalent control strategy. And this works similar to the ankle strategy that's dominant in the sagittal plane of standing balance. A strong handstand balances in a straight body line with minimal joint displacement. And weaker handstands may require compensatory torques, such as a shoulder or a hip strategy. So while control strategy has been determined in terms of torques required to control the center of mass, the underlying motor control mechanism produced by muscle and joint organization has not been established, and we aim to begin establishing that link in this work. Therefore, the aim of this study was to explore motor control mechanisms of handstand balance by first determining the variabilities of joint angles and center of mass position over the course of balanced 30-second handstands, and second, exploring which joint angular variabilities contribute to center of mass balance through the use of multiple linear regression models. And these aims together serve the purpose of increasing understanding of joint contribution to global variability in the handstand. So to obtain our study goal, we recruited competitive gymnasts in the USA Gymnastics Development Program. They were between the ages of 7 to 13, and all of them had the ability to hold a 30-second handstand on both floor and beam surfaces. This presentation is reporting data from 3 of these gymnasts, and we did collect 10 total gymnasts that we're working on analyzing now. For our data collection, subjects came to the University of Denver Human Dynamics Lab, where they performed a 30-second floor handstand over forced platforms with a full body marker set. And this was part of a larger 7-task standing and handstand protocol that they all were a part of. We modeled the gymnast as a 14-segment body, where joint angles in flexion extension and ab adduction were measured on both sides of the body independently. And we also determined center of mass position in both the ML and AP plane. And again, our goal with this data is to determine if we can predict center of mass position from the variability of these joint angles. This is an example of flexion extension joint angles for one gymnast during a 30-second handstand. On this graph, the x-axis is time, showing that the gymnast held the handstand for the full 30 seconds. And the y-axis is joint angle, where positive is flexion and negative is extension. And we see that over the course of the handstand, most joint angles have very low variability. And we do see one instance of musculoskeletal redundancy right after that 20-second mark, where when the elbow flexes, the shoulder closes, but both joints are able to return to their equilibrium value following this. And this is a plot of the center of mass and center of pressure in the AP plane for the same trial as that previous slide. And both center of mass and center of pressure on the y-axis are plotted against handstand time on the x-axis. And here we see a pattern typical of quiet stance, where it's believed that the center of pressure tracks the center of mass and oscillates on either side to stabilize around some central position. And in our work, we used coefficient of variation as a measure of variability. And here we see a single subject example of CV shown as a % on the y-axis in the AP plane for all variables. And consistently for all 3 subjects, joint angle CV was higher for all joints on both sides of the body with respect to COM and COP. And this increased variability at the joint level confirms that there are many functional degrees of freedom necessary to control the center of mass, and that athletes are continuously self-organizing their joints to balance. Next, we ran multiple linear regression analyses by using joint angle variabilities as predictor variables for center of mass position on either the ML or AP plane. Our basic function used joint angles as predictor variables for center of mass position. And more specifically, we used wrist, elbow, shoulder, and hip joint angles on both the left and right sides of the body in both flexion, extension, and abduction for each joint. So this meant a total of 4 variables for each joint and a total of 16 predictor variables for COM position. And we ran regression models for COM ML and COM AP separately. In this example, we see that the model fits the data well with an R-squared of 0.86, indicating that joint angle variabilities may predict COM ML position. Okay, and I'd like to take some time to walk you through our results table here. So using standardized coefficients, we converted our joint angle variability contributions to a percent, and that's what we're seeing here in this table. So the results from subject 1 are in green, subject 2 are in blue, and subject 3 are in yellow. Each subject has 2 models that were ran for them, where joint angle variabilities on the left and right sides of the body in both flexion extension and abduction. So those 16 variables that we talked about are regressed first against COM along the ML axis, and then COM along the AP axis. And for all subjects, we see quite consistently that shoulder flexion extension is a major contributor to COM position. And we also see some subject-specific control strategies in the other highlighted cells where a contribution over 10% is highlighted. So for example, in subject 1, we see some elbow contribution, and in subject 2, we see some wrist contribution. And as a summary of the results, we summed joint angle contributions across the left and right sides of the body and averaged them across subjects to get this figure. And as before, we see that the shoulder joint is the major contributor to COM balance in both of these planes. And consistently in both planes, the shoulder contribution is followed by the elbow and then the wrist and finally the hip. So to sum it up, we found that joint angle variability is consistently greater than COM variability, and this indicates a joint-based motor control strategy. And we saw that shoulder joint motion was predominantly related to the collective movement of COM in both the AP and ML planes. And this indicates that training strategies should consider utilizing shoulder strengthening drills to improve handstand body line and balance. Our current work is analyzing our expanded cohort of our N=10, and we're also working on a comparison of the handstand to a standing pose. So with that, I'd like to thank you for your attention and open the floor to questions.
Great, thank you so much, Moira. Do we have any questions from the audience? Give me a moment to see if we have any pop into the chat. Do you anticipate that you'll have, I guess, the same findings across when you start, I guess, when you add the rest of the participants? Do you think this will be a pretty like a firm finding that you'll have the consistently more variability in that shoulder joint compared to all other joints, and that it'll be a joint level? What was the control mechanism? Sorry.
Yeah. Well, I was interested to see the shoulder joint contributing the most. It does make a little bit of sense, but I was expecting the wrist to contribute a little more based on that ankle control strategy we see in standing balance. But it is interesting that shoulders, which are a larger muscle than the wrist, may contribute more to this strategy.
And will you say that this will have any practical implications, I guess, for the training? Do gymnasts currently target their shoulders for improving the handstand, or is that sort of something that's going to be a bit of a novel finding for them?
From what I've seen, a lot of successful coaches do target the shoulders, but a lot of coaches that aren't as experienced wouldn't know this right off the bat. So hopefully, if this finding persists through all of our subjects, all coaches will be able to use it in their training.
Yeah. Be interesting maybe to implement a bit of a training intervention off the back of it if the finding is consistent.
That would be great.
Yeah. Do we have any questions from our audience? If not, we can wrap up this session. Just give it a moment. Sorry. That seems like it's it for today. So thank you all so much. And thank you to our presenters, Harper, Emily, Casey and Moira for their presentations. I'm sure that if you have any questions, they would be happy to answer those via the chat or through email. So thank you all so much. And I hope you enjoy the rest of the conference.